So you want to create a computer game. In this case, you're on a very interesting journey because there is a huge market. People of various ages, starting from like 5 years all the way to 90 and 100 years. They are playing different genres. Candy Crush, Minecraft, World of Warcraft, Counter-Strike, and so on. You can create either two-dimensional games. A good example would be Clash of Clans, which runs on mobile devices. Or a game about creating something, like the iconic Minecraft. If the game is interesting, you'll be able to monetize it, which can be a great source of passive income. And the only requirement would be to make your game interesting and enticing, so the players remain engaged within it. You have to understand for whom you are creating the game. For example, World of Warcraft, created all the way back in 2004, lasted for more than 20 years and encountered millions of players who joined together to fight monsters on a vast scale. It was a very big game, but nowadays, especially with the help of AI, we're able to iterate very quickly. And even if we're not going to be able to make huge games, similar to World of Warcraft, we can create very enticing ones, even as indie developers, or even as a one-man army. Regardless of the idea and which style we pick, all of the games are united under one idea. They are programs which are meant to run on digital devices, like mobile phones or computers. And all the games combine various things: the graphics, the sound, the gameplay, and the interaction with player. For the graphics, when we're looking at World of Warcraft, it looks hand-painted, which is a very appealing art style that has inspired many artists throughout the years. Looking at things like Minecraft, it is all about the blocks and the square stuff. So even if we look at the moon or the sun, they are rectangular. And despite that, the graphics, the visuals of this game can be quite stunning. The next core component, the sounds, is also very important because it adds immersiveness. And properly crafted sounds accentuate various important moments in the game. For example, when you're fighting a boss, you might not even have realized that the special suspense music has been playing all along, because you were so immersed in the game, and the music made you feel even more involved. And only say, after you've defeated the boss, the music stops, and you might notice a transition. Besides the music, the special sound effects, the SFX so-called, the clashing of the swords, shooting, and so on, those are all mini sounds, which can be just as important because player hears them quite often, especially if it's sounds of footsteps, for instance. So they have to be carefully selected, not to be too repetitive or boring. The rules, the gameplay, the idea of the game is the next core thing. For example, in World of Warcraft, it's all about growing your character, much like a Tamagotchi back in the days, where you start at the level 1 and continuously progress your character, acquiring powerful gear, putting it on your character, and becoming stronger and being able to fight further creatures in other locations of the continent. Or in the case of Minecraft, it's about starting with nothing, crafting an axe, chopping down the tree, getting stone with a pickaxe, and building houses and structures and various tools, so you interact with the world. And then eventually you're able to defeat a final boss, the Ender Dragon. And back in the days when I was playing Minecraft, the Ender Dragon wasn't even there. And yet, Minecraft was very popular even back then, without a clear defined goal, because the idea of the game implicitly is about creating things. It's much like Lego. The core idea, the gameplay of Minecraft, is about letting players express themselves through creating something. The player input, how stuff is being controlled within the game as you press buttons, is also important. And even things that you might not have expected, like how does the camera move around the player, or how does the player remain visible when there is a wall between the camera and the figure of our character. Do we move the camera forwards to remain in front of the wall so that we keep seeing the character? Or do we find some other tricks? It's important to make sure those things fit together. So in this course, we'll have an overall look at various tools and the techniques you'll be encountering along your journey. Back in the days, when you wanted to create a computer game, there was no tools to help you, apart from very basic things, like a notepad to code, graphics libraries that would allow you to show things on the screen with very vague documentation. If there was any documentation at all, you'd be quite lucky. So to create a game like Half-Life, for example, you'd have to spend a lot of time learning about very complex math concepts before you could even show something on the screen. You'd have to build tools on top of that to move camera, to navigate player, to give color to your 3D objects, script all of the lighting interactions and how the shadows land on different surfaces. Nowadays you don't have to care about that too much, because we're already being given a pre-built set of tools that was fine-tuned and crafted over the years by very clever teams. Those tools are the game engines. The game engine is essentially another program which helps you to build your own program, your own computer game. The game engines neatly combine the aspects of writing the code, with positioning different graphics, arranging them within the scenes, quickly setting up the direction of the light, and allow you to create a playable environment much quicker than if you were to start from complete scratch. So to save yourself a ton of time, it would be wise to pick a game engine in which you would want to work, and then use its features to bring your ideas into life much quicker. My personal favorite one is Unity, in which we can create 2-dimensional or 3D games for mobile phones, consoles, and computers. There are other alternatives, like the famous Unreal Engine, which is known for its excellent and various forms of high-quality graphics. Another cool thing about Unreal Engine is that you could script interactions between the things in the game through a series of graphs, which you could visually connect and form a logical group out of them to describe how various things should function. So it's a form of visual scripting, but if you're into programming, Unreal Engine allows you to code in C++, which opens a huge amount of possibilities for you. Another powerful option, especially if you're interested in 2D game development without diving deep into programming, is Construct. Think of Construct as a visual composition tool. Instead of writing traditional code, you create games similar to building with digital building blocks. What makes Construct particularly appealing for beginners is that you see is what you get approach. You can drag and drop elements on your game screen, set up behaviors using visual logic blocks, and see your changes instantly. Games like the Next Penelope and Airships Conquer the Skies were created using Construct, showing that you can create polished, professional games with this engine. While Unity and Unreal are like fully equipped workshops with every tools imaginable, Construct is more like a specialized crafting table. It's designed specifically for 2D games and web-based projects. Its subscription-based model includes regular updates and a vast library of pre-made behaviors and effects, if you want to focus on game design concepts instead of programming syntax. I also have to mention an important thing, that Unity was used to build a very popular Chinese game, Genshin Impact, and was probably chosen as the game engine because of its vast set of features. Besides of being able to set up the gameplay, you also have an ability to extend the engine beyond of its capabilities. You're able to adjust the visual side of the game, how stuff appears on your screen, how it's rendered, through the stuff like scriptable pipeline, which is one of the features in Unity, meaning that you can specify your own code to adjust the logic, and you're able to connect powerful libraries for networking, as well as an ability to support a huge world of Genshin. Unity Game Engine is able to tackle all of that and even more. You script logic using a particular language, C#, which is modern, flexible, and not too overly complex, automatically manages memory, which means that if you are mentioning certain things in your code, or incarnating certain things within your game, it is then efficiently able to clean up the things that you no longer need and to give back the resources to the computer. By expressing its logic through the C# programming language, Unity became even more popular among the developers. So to conclude, it's important to select one game engine, because we want to get to making a game straight away, instead of focusing on the low-level engineering of things, or on crafting tools that already exist. If you fall in love with this subject, of course you'll be able to specialize on various things, such as computer graphics, physics, AI, character navigation, optimization techniques, and so on. Let's look at one of the most popular examples, the game Mario Bros, which was made in 1985, so quite a long time ago. It has several important features, like jumping, avoiding obstacles and monsters, collecting points, and getting from start to finish. It was made for pretty old consoles, so it had to be simple in order to run on such a hardware. It is a collection of pictures, we also call them sprites, which are arranged relative to each other in a two-dimensional space. For example, as the Mario jumps on these green platforms, we can see that the picture of Mario is being moved or displaced up and down. We're also able to shoot things, and that process is just another movement of another picture. Any kind of creatures we see and observe within the game, they're also sprites, the images. As we're playing the game, we don't really care about the fact that they are images, we perceive them as enemies or allies. Essentially, to make a game like Mario Bros, we want to make sure that we are swapping the images and moving them appropriately, showing the scores and not letting the picture of Mario to overlap with images of obstacles or enemy images. This touches on the concept of physics, allowing the Mario character to collide with things, and in this case, physics are very simple. Essentially, they're just comparing the size of the picture in pixels and making sure that there is appropriate offset between the picture of the green platform, for example, and the picture of our main character. Some objects or entities Mario can overlap, which allows him, for example, to enter the castle at the very end, because he's not colliding with the picture of the castle. The image of Mario is being painted sort of on top of the castle. And once again, as we reach the end, it appears as if Mario has entered the castle, but in reality, we've simply turned off its picture. 2D games like these rely on a sequence of sprites. For example, if we look at these sprites, we can see the animation of walking, of running, and stuff like jumping. So by switching them around very quickly, we can get an appearance of Mario running around and doing things. But in essence, we're simply flipping between those images sequentially. Back then, the memory constraints, the amount of information that you can hold on the device, was very much constrained. So the sizes of those images are tiny, and the color palette is quite simple. Nonetheless, with all of those interactions, we're able to create an enticing game, which gives the sense of adventure to so many players. Overall, we can dissect any kind of game into a background, series of images that are behind everything, behind our main character, the stuff in the middle, for example the platforms, the enemies, and our main character, and also the foreground. Those are typically the most important elements, such as scores and buttons. By overlaying them on top of each other like this in a sequence, we can get cool effects. And for two-dimensional games, if we go a step further, we can take the background, for example, and make it itself consist of several layers. This allows us to achieve a parallax effect, where we have a composite background consisting of multiple images that slide relative to each other at different speeds. This gives us an illusion of depth, distance, and volume, all of that while the game still remains two-dimensional. 2D games can be quite complex to make, because they have their own tricks, the two-dimensional lighting, the two-dimensional shadows, camera movement, and so on, but overall 2D can give you a very simple start, because you don't have to care about many things, such as the 3D physics, the collisions, the navigation of characters through the complex 3D environments. The performance implications are usually out of the way, but if you're considering whether you want to do 2D or 3D, I would really say think about what you want to make, the artistic style of your game, the gameplay, and then from there select whether you want to go into 2D or 3D, because each one has its own challenges and each one can be just as interesting. So now, having considered the Super Mario Bros., let's check out the 3D version of this game, the Super Mario 64, which was made for Nintendo consoles and is using 3D geometry to give us the volume and the ability to travel through the level in various ways, not just left and right, up and down. Just as in the 2D version of the game, the mechanics mostly revolve around jumping the panels, collecting the coins and the stars, and making sure we don't fall off, otherwise we'll lose health. We can separate the game visually into two parts, the game itself, with the character running around, and the numbers with icons added on top of it. So literally two layers. The first one, the three-dimensional, is achieved by drawing different objects. For example, if we look at the platforms, they're simple stretched cubes with some coloring added to them. The cubes themselves are defined by vertices, the coordinates, which tell exactly what shape the surface of the object has and where it's positioned, while the coloring is applied on the surfaces defined by those coordinates, making the object look more interesting and natural. The three-dimensional coordinates, the points, form a so-called mesh, because they all interconnect and create a volumetric surface, while the second thing, the coloring, is done by textures. Texture is a two-dimensional image which kind of wraps around the three-dimensional object. Depending on the type of the texture, you're able to make certain objects look like stone, the wood, the carpet, and so on. So literally two things, the meshes and the textures. Another important aspect that we see is the shading on the Mario. If we look at his head, we observe that it's brighter when it's closer to the camera and darker at the edges. So we're getting this effect that is commonly referred to as the Phong shading. By looking at an image of a sphere, Phong shading allows us to shade the object to turn it from a circle into a sphere that has a volume. In computer graphics, that's a very cheap effect to achieve, so we see it employed in this early game. We can also check that no matter where Mario is, the camera follows it around, kind of like on a selfie stick. But the camera is slightly more clever, because if the Super Mario makes an abrupt movement, the camera has a smoothing effect. So it will not immediately follow the character, but will have some kind of buffer zone or the delay. That is important for the comfort of the game, so that it doesn't look too jerky. We can see that the game is quite simple. It doesn't have any complex lighting effects that we would see in modern games, just a simple Phong shading and a circular shadow. The shadow, despite being so simple, plays a very important role, Because by looking at the shadow, when the character is jumping, we're able to judge exactly where Mario is in the space. If we were to remove this shadow, then when we travel between panels, we would have a hard time understanding where the character is, and would likely miss the panels more frequently. This detail is quite important, but normally players don't think about it, yet if you were to remove it, you would immediately notice the difference. A slightly more complex game, at least visually, is the Crash Bandicoot. It's the one where you run around via Coyote, or the fox, defeat enemies, and collect points. What I like about this game is the visual appearance. It's still quite simple, uses simple objects with very few coordinates, doesn't use complex lighting, and the character also has the circular shadow, similar to a Mario 64 game. In the bonus levels, when Crash Bandicoot has to go from start to finish, from left to right, we can see that it employs the effect of parallax background for the trees, but also remains three-dimensional. The overall style of the game is kept congruent because, first of all of the objects maintain a similar level of detailization. None of them are more detailed than the others. Nothing really sticks out and everything belongs together. For example, if you look at the turtles or the character itself, they have the same amount of detailization. Looking at the decorations, the walls, the grass, and the platforms, they all have the same resolution and everything fits together nicely. That's especially important because nowadays, with asset store and the ability of purchasing assets and pre-made decorations from other artists, you might end up in a situation where they create a disjoint look and don't fit together. Crash Bandicoot doesn't have this issue because everything is made in the same artistic style with the same idea kept throughout. When the character navigates the 3D environment, we're moving its surfaces, its coordinates out of which it's made, relative to the other coordinates of the decorations. This is somewhat similar to the two-dimensional game where we were moving the images relative to each other. Here it's just three-dimensional surfaces that are being displaced. The 3D games have the concept of three-dimensional rotation. Besides of being able to spin clockwise and counterclockwise, objects are also able to tilt towards us and away from us, as well as spin. These things require more complex physics, but given that you're using a pre-made engine like Unity, all of those things should be already taken care of for you. So far, mostly we've been looking at theory, but now let's have a more practical, hands-on experience of what the game engine is. For this, let's consider Unity. This engine consists of several controls and several panels. On the left we have the hierarchy, which contains all of the currently existing objects in the scene. The scene is right here, and I can look around by pressing and holding the right mouse button and dragging it around to check out what's happening around me. While holding the right mouse button, I can also press WASD keys to fly in and out. I can click on things and then press F to focus on them, and while focused and while holding Alt, left mouse drag to orbit around the object. With this object selected, I can see certain properties in the panel on the right, in the inspector. It has several scripts attached on it. We also call them components. The transform component, the mesh filter, and the mesh renderer component. So 3 in total. The mesh filter contains the collection of coordinates, the vertices. It contains the description of a mesh. And the mesh renderer almost always accompanies the mesh filter. They go together because the mesh renderer makes those coordinates visible. The mesh renderer usually works with a material, which you can expand in here and see that it's one thing. The material is like a container for texture, a container for a two-dimensional image, or several of them. So if I click here, I can see that this particular material currently applied on this object contains several slots for different two-dimensional images, and we see that this one, called albedo, is already being plugged into it. So I can double-click on it, and you can see that it's a two-dimensional image, which is designed in a special way so that it can be applied onto various objects. And in particular, you can see and recognize certain things, like different benches, the fences, the barrel is right here. So we can take this image and literally apply it on multiple objects, and it will still work. So we take the two-dimensional image, plug it into the material, apply the material into the mesh renderer slot here, and make sure that these two components, the mesh filter describing the coordinates and the mesh renderer describing which material it wants to use, they go together on this entire game object. So I can take this thing, and with the move tool, I can take it and drag it around. I can also click on other objects on this pile of logs. Just clicking on this little tiny green square allows me to move it in the horizontal plane. There is also the blue square, so if I carefully click on the blue square, I'm able to move it in this plane. And then also there is this red square, which might not be very visible, but I'm just going to turn it around like that. And by clicking on this red square, I'm able to move it along this plane. So it's quite convenient, and by changing the scale of the object, I can make it bigger. So I can click on this button, click in the middle, in the center, and grow it in and out. Because this object is selected, I can see it being highlighted in the hierarchy. And if I scroll up, we can see that the pile of wood, the pile of wood 01, the lantern and everything, they are the children of the house 1 object, because they're kind of indented to the right. I can click on this triangle and collapse the whole thing, and we can see that all of them have been collapsed and hidden inside of here. By clicking on the house 1, I'm gonna see that the entire thing is being selected now, because it nests all of the different meshes and all of the different game objects. I can take this move tool, and with the house 1 selected, I can take it and drag it around. Be careful, because if you've accidentally clicked on one of those things, the 2 buttons here, you're either going to hide the object temporarily, or you're going to prevent it from being clickable. So if you clicked here accidentally, by clicking on various objects, no matter how much you click on the house, you won't be able to select it. I can also rotate the object by clicking here. And similar to the move tool, there are 3 different axes around which I can rotate. Anything that's inside of this project panel still technically doesn't exist in the scene. It's not incarnated. But I could go ahead and find one of the meshes, for example this sack or the barrel, and literally drag and drop it into the scene here. Now I brought it into the existence, and it starts to exist in the world here. Currently it has just a simple plain material, and if I expand it, you'll see that it doesn't contain any kind of images, and in fact if I were to try and stick some kind of image into this slot, it wouldn't let me. Because this is a default preview material, we would need to right-click somewhere in the project panel to create a material. Let's call this one barrel material, and I can drag and drop it onto the barrel. Visually nothing has changed, but because this is a custom material, by clicking on the barrel, I'm going to be able to now expand it and apply any kind of texture on it. So I can click on this tiny circle, and we can see that this one works quite well. So I'm going to double click here, and now it's loaded into the color slot of the material. Of course, this is just a tiny glimpse into the power of Unity. As you start studying the aspects of this wonderful engine, you'll learn about scripts and the ability to create your own components. So for example, your own custom things that you can stick on the object, and inside of such scripts define a logic that, for example, allows you to move various things in the world by simply pressing on your keyboard buttons. That's also how we're able to move characters around and to look around with the camera. In this section, I want to return back to Unity and talk about the character animations, because that's a very important aspect, and in the games that we've been discussing today, characters take a central role. Their particular feature is that their bodies are organic. So this means that when they bend their arms or legs, they deform in a soft way. If I go ahead and in the project panel find a scene for the military, double click it, I can fly around, so hold right mouse button and use WASD, and look at various objects located here. I can see that there are different characters, this military guy, as well as other examples. So in the hierarchy, I can click here, hover my mouse over the scene window, and press F to focus on it, and Alt left mouse drag to orbit around. So we can see different variants of this character, but one characteristic is that they're all organic, and they are humanoids, so their skeletons are similar. If I click on the triangle here, click on the root, on the pelvis, and for example on the spine, by taking the rotation tool, I'm able to take this bone and rotate it. And you can see that the bone is driving the entire shell, the entire collection of vertices, the coordinates, around itself. So we can rotate this spine to a certain degree, but it's gonna start to break down after a particular limit. And in the bends like these, especially visible if we do it on the legs or the arms, these kind of bends can pose an issue, but usually we don't notice those problems. So we can see that this cuff bone is the child of the thigh bone, located slightly higher here. The thigh bone is able to drive the cuff bone, but each bone controls a set of vertices around it. So the cuff bone that I had selected a moment ago, it was influencing the vertices in this region. And the thigh bone cares about driving the vertices, the coordinates, and the polygons in this region. So an interesting thing happens for the vertices that are in between, because those two bones, both control these points in here. And in fact, this kind of mutual control is what allows those points located at the joint to respect both bones and to have a soft bend right here. Also, we can notice this effect around the knee, because this vertex here isn't pulled as vigorously as those ones around the shin, but it's still being pulled somewhat. That's because this vertex not only listens to the cuff bone, but to the thigh bone. So this type of surface is still 3D. It consists of vertices, but it has slightly more intricate structure than, say, simple things like those cubes, which are also made of points. The difference is that this model has the vertices listening to the game objects, the so-called bones. And the process of binding vertices to such bones is called rigging. Artists spend a good time designing the actual shell of the character, and then spend a good portion of time tying the vertices of this shell to the bones. So they spend time rigging this character. This then allows the artists to animate the bones and to make the character run, for example, because it would be very tedious to animate every single vertex from which this character is made. If I enable the wireframe mode, or the shaded wireframe, you'll see that there is plenty of vertices here. And my guess is that this character is made of at least 10,000 vertices, maybe 20,000. So by binding those vertices in groups to the bones, and then just animating the bones themselves, we're saving ourselves a ton of time. If I go ahead and click on this button, I'm going to start the play mode, and we're going to switch into the game window. The mouse will hide. To unhide it, we can press escape. But right now I just want to show that we can rotate the camera using one of the custom scripts, the custom components, and we're also able to run around. So by moving the character like so, I'm able to blend between different animations. Currently I'm pressing the sideways motion and moving him to the right. He's just walking, but if I press the shift key, the character will start to run. So we're blending between different animations, and we're doing this seamlessly because the animation controller component that is sitting on this game object is doing its job properly. By blending the animations smoothly, we're able to transition between various things, between jumping, walking, running, and fighting. Now we're going to look at how even the biggest games started as really simple prototypes. You might think that successful games were always polished and beautiful, but I'm going to show you something that might surprise you, how rough and basic they looked at the start. And this is super important because many beginners think they need to make everything perfect from day one. But that's not true at all. It's important we iterate quickly to find out exactly which parts are most enjoyable and important for our game. The 20-80 rule, also known as the Pareto principle, states that roughly 80% of effects come from the 20% of causes. For us, this means that only 20% of our game's features will typically create 80% of the player's enjoyment. So we should find out exactly which thing is the most important about our game and focus most of our efforts into that region. So let's start with Minecraft, possibly one of the most successful games ever made. You know it today as a huge world where you can build anything, fight monsters, and explore endless landscapes. But back in 2009, when Marcus Persson, also known as Notch, first started, this game was completely different. He actually built the first version in just 6 days. Can you believe that? It was just a bunch of grey blocks. No fancy textures, no inventory system, definitely no crafting. Just blocks that you could place and destroy. Notch wasn't even sure what kind of game it would become. He just had this basic idea, what if players could build stuff in the 3D world? But here is where it gets really interesting. Instead of waiting until everything was perfect, he released this super basic version to players right away. And something amazing happened. Players started to give all sorts of feedback to Notch. They'd say things like, hey, what if we could craft items? Or what if there were monsters at night? Or could we have different types of blocks? And Notch did something really smart. Instead of trying to add everything at once, he added features one at a time. First, he added different types of blocks, not just grey ones anymore. Then he thought, okay, what if players could craft things? So he added basic crafting. Then came the survival elements, having health, needing to eat, and so on. In fact, as I remember, the eating component and the experience came only after a few years since the game release, so it definitely was a long time. Anyway, finally he added monsters and the mining parts. Each time he added something, he would let his players try it out. Some ideas worked great, others needed changing. But because he started so simple, he could easily adjust things based on what players actually wanted and actually enjoyed. Another massive game is World of Warcraft. You know today as also a huge and beautiful world with amazing landscapes and epic battles. But back then, when they first started testing it, the whole world was just basically a flat piece of land with some boxes for buildings. The developers at Blizzard did something really clever. Instead of trying to make everything beautiful at first, they focused on the most important thing: how the game felt to play. They had those super basic character models. They spent weeks just testing things like how fast should players run, how high should they jump, how should the camera move when you're running around, and so on. They didn't even have proper monsters at first. The first version of combat was hilarious. You just click on the cube-shaped enemies and watch the numbers pop up. No fancy animations, no epic sounds, no effects, just cubes and numbers. But this was actually smart because it let them focus on one critical question: is this fun to play? The really interesting part about World of Warcraft and its early development was how they tested the social aspects. Testing things like how far should players be able to see each other, how should the group mechanics work, what's the best way to communicate with the other players. They actually scrapped the entire features they thought they'd spent months on developing, simply because when they tested them in this basic version, they weren't fun. Better to find that out with a bunch of boxes than after making everything look beautiful, right? So what's the big lesson here? Every amazing game you've ever played started as something super basic. The key is to start with a core idea, the thing that makes your game unique and fun, and test that out first. Don't worry about making things look pretty. Don't worry about having every feature. Just focus on the basics. Think about it this way: if your game is not fun when it's made of basic shape, adding fancy graphics won't make it better. But if it's fun with just boxes and basic controls, imagine how great it will be when you add all the cool stuff later. So, to conclude, start super simple, literally as simple as you can make it. Test the most important part of your game first. Get feedback early. Don't wait until everything is perfect, else you might invest a lot of efforts into something unnecessary. Remember that anytime you can save during the development, you're able to invest into the remaining important 20%. That's the key to success. Add features one at a time. Test each addition, and don't worry if things look ugly at first. Nearly every game started this way. This time let's dive into how multiplayer games actually work under the hood. When you're playing an online game, there's a whole system of communication happening behind the scenes that makes everything work together. In a multiplayer game like Minecraft, every action needs to be communicated between players. When you place a block, mine resources, or move around, this information needs to reach every other player in the game. But the process isn't as straightforward as you might think. The first thing we need to understand is the basic structure. There is the server that acts as a central point of communication, and then there are clients. For example, your computer could be a client. Think of the server as a central hub to which the players connect, rather than players trying to connect directly to each other. If they were to connect, then this would be the fastest form of communication, also known as peer-to-peer, but this approach is susceptible to cheating. If we introduce this middle point, the server, then the server has a chance to validate the actions of each player before showing it to other clients, the other players. Once again, at the cost of extra latency. So, the server's main job is maintaining the authoritative state of the game. So the server computer acts as an authority. It means that the server keeps track of what's actually happening. When you perform the action, the client sends that information to the server, it validates it, and then broadcasts it to other players. Besides preventing cheating, this also makes sure that everyone is synchronized. Now, here is where things get interesting. We have this latency problem, the lags. You've probably already experienced this in the past. For example, in the shooter game, if you fire at someone, like in the Counter-Strike, but nothing happens, or players seem to teleport around instead of moving smoothly. This happens because there is a delay between your computer and the moment when you fire, and the time when the server actually receives this thing from you and realizes that, oh, this player has actually shot, I should probably broadcast. So it's important to hide this latency, because if it takes, for example, a quarter of a second for the message to reach the server from you, and then another, let's say, quarter of a second to reach every single player, then on average that's almost half a second. And if players are running around, like in Counter-Strike, things can be completely different on various computers of players. So to deal with the latency, games use various techniques. One of the most common one is the client-side prediction. Your game doesn't wait for the server to confirm every single action that you did. Instead, you see the results immediately on your computer while waiting for the server confirmation. If the server then comes back with a different information, your version of the game has to reconcile these differences, which can sometimes lead to those weird moments where characters suddenly jump or snap around. That's because the prediction on your side was wrong and the server forced you to reconcile the changes. Let's look at how different games handle those networking challenges. In a fast-paced game like Counter-Strike, precise timing and positions are crucial. The game has to carefully balance the responsive gameplay with accurate hit detection. And in MMOs like World of Warcraft, the game allows slightly more freedom about the exact placements of the characters, because split-second accuracy typically isn't important in those MMOs. Instead, they focus on maintaining consistent game state across thousands of players. For example, by placing them into specialized rooms, like invisible sections of the world, and synchronize between players while they are inside of those regions. When we're using spells, we often see the casting bars, and those aren't just for the show or to annoy us. The casting bars actually help us mask the network latency by giving the server enough time to validate the actions and to synchronize them across all players. If you ever wondered why most MMOs have ability cooldowns and cast times, that is mostly the reason, to hide the latency. The toughest situation is possibly with the racing games, because those ones need extremely precise position tracking, and if the cars aren't exactly where they appear to be, the whole experience basically falls apart. That's why many racing games use specialized networking code to maintain precise positioning while still feeling responsive. On a basic level, there are two approaches of communicating information. There is the TCP networking, which is the slow but very reliable way of transferring data between you and the server, and there is also UDP. That one is like firing lots of information bits at the server, like almost flooding it with the information. We don't wait for the confirmation from the server, but simply send a whole barrage of information. This makes sure that the packets reach the server very quickly, but can be significantly more expensive. In this UDP approach, certain packets might get lost, but because we're flooding the server with them, some of them will definitely reach it. It's very useful for shooting, and is also used in the racing games. Overall, the real art of multiplayer game development is making all of this invisible to the player. When this works well, you don't even think about the complex system of communication that happens between every action. But when it doesn't work well, that's when you notice the lag, the snapping, the rubber banding, or the desynchronization. Welcome back. Over those videos, we've explored everything from basic game concepts to networking. Let's quickly recap what we've learned. We started out by breaking down games into their basic parts, and now we know that every game needs a game engine to help us avoid creating already existing tools. That way we're able to focus on creating our game straight away. We've learned that each game has to have clear gameplay mechanics and rules. We've looked at the 2D versus 3D graphics approach, and also the player input and how they interact with the game. We've checked out the user interface and its importance to show visual elements on the screen such as health points, score, and so on. And we've also looked at the animation, the rigging of the characters, as well as discussed the multiplayer, which helps us to make players enjoy the game together. Each of those pieces are important, and now you know how each one fits into the bigger picture. At the end, let's look at 3 different types of games that can serve as a good inspiration for your first project. The first one, a platformer type. The game called Only Up became a massive hit in 2023, but its core mechanic is very simple, jumping from point A to point B. When you strip away the complex visuals, you're left with fundamentals that teach you the physics, the player controls, and the camera systems. By looking at this game, we see that your first platformer doesn't need to have hundreds of levels. Just focus on making one jump feel satisfying. Second type of game is the card games. Take the game called Inscription. Under its atmospheric horror, it's a system of numbers and rules. Starting with a card game can be very good because it teaches you crucial programming concepts, the state management, turn systems, and how to design user interface. Plus, you can test gameplay with paper cards before even writing any code. The third example of a game are scary and short first-person games, like Fears to Fathom. Those games have an interesting story, quote-unquote, based on real events. These are perfect for learning 3D development because you can focus on atmosphere without complex character graphics. These games look so simple, and in fact, that's why Fears to Fathom looks so attractive, because of its simplicity. It makes us feel like we're back a few decades, which makes it even more compelling and immersive. By making a similar game, you'll learn how to build a small set of scenes, how to trigger character conversations, and most importantly, how to tell a scary story. Now let's talk about the learning steps that you can take next. There are 3 of them. Choose your learning path. If you pick platformer, Focus on physics and the controls, the keyboard and mouse and the camera. For the card games, start with a basic user interface and with basic rules to make sure that your game is interesting. And for first-person games, probably the most important thing would be learning about 3D space, the sound, and the triggering of conversations between the players. The second part is to pick your game engine based on your goals. My personal favorite is Unity for its versatility and massive learning resources. You could also pick Unreal for its graphics. Select the Go.engine for its open source approach with a supportive community. Open source means that you can read the code and access it, and if you find something is missing, you can add your own code and then attempt to make it part of the Go.engine as its default feature. Of course, to be accepted, you'll have to have adequate programming skills, but it's worth considering in the long term. Or the fourth engine, the Construct for rapid 2D games development. And lastly, the third part is start with the basics. Start watching tutorials for your chosen engine, build a small prototype, and join the engine's official forums or the subreddits on reddit.com or Discord to find like-minded people and to learn from them. Most importantly, learn by doing. Each game we discussed started as something tiny. Only Up began as a simple jump mechanics, Inscription started as a basic card rules, Fears to Fathom began with the atmosphere tests in a single room. Remember that your first game won't necessarily be your best game, but it will be the most important one you make. Every developer you might admire started with something simple. The tools and concepts we've discussed are your foundation. Now it's time to dive into the technicalities and get to building. My personal advice would be to begin with a 2D game. That's why the continuation of this course, the second part, will be about making a two-dimensional game in Unity, and specifically we'll be using the latest Unity 6 version. It will be quite fun and a hands-on experience, so I'll see you there. My name is Igor, I wish you good luck and see you soon.